So with the exact numbers, it was pretty straightforward. If you can count the number, or you can count the quantity to get the number, then it's exact. It means it has what we call infinite number of significant figures. And if it's a conversion factor within the same system of measurement, those are also exact numbers. So those are only two criteria for exact numbers. And so all other numbers are what we call measured numbers. And so with measured numbers, as we learned in last lecture, you have to use a device to obtain the value. Now, depending on the device you use, you get some type of uncertainty in the measurement. And so all measurements that you make contain certain digits plus one uncertain digit. And we'll look at how you determine the number of significant figures when you're doing an actual measurement a little bit later. But when you have a measured number and you want to determine, what digits are significant, there are a few rules that we look at. And so the first rule is fairly straightforward. Any digit that's a non-zero digit is significant. So any number 1 through 9 that you see in a measurement, that is a significant figure. Secondly, all numbers in scientific notation are significant. So whether they're zeros or non-zero, they're significant. So if I wrote 1.03 times 10 to the 5th, this would have 3 significant figures, because both zeros and non-zeros are significant in scientific notation. Then we get to exact numbers, and with exact numbers, they have what we call unlimited or infinite number of significant figures. And so again, these are numbers that we obtain by counting, or conversion factors within the same system of measurement. Now, the only conversion factor that's from metric to English is this inch to centimeter that's exact. All other metric to English conversion factors are not exact numbers. And so what do we mean by exact? So for example, we say there's 3 apples. Well, we know there's 3.0000 all the way to infinity apples. So the zeros keep on going. So we know exactly that there's 3 apples. Now, where the discrepancy comes from is when we have zeros. So we said when zeros are in scientific notation, they're significant. But other than that, we have 3 different types of zeros. The first one is a leading zero. And with leading zeros, these precede the first non-zero digit, and these are insignificant. So here, if we look at this number 0.0035, the zeros in front of the first non-zero number are not significant. So anytime you see a number less than 1, the zeros that precede the first non-zero number are not significant figures. You don't count them. Likewise, another type of zero we have is captive zeros. So captive zeros are between 2 non-zero digits. So these 2 zeros between 2 and 3 are significant because they're contained between 2 non-zero digits. So anytime you see a captive zero, they're significant. Now with trailing zeros, or what we refer to as placeholding zeros, and so these come to the right of the last non-zero digit, or yes. And so these are significant only if a decimal point is present. So in the first example, we have 100, but with no decimal point. So since it's 100 with no decimal point, those trailing zeros are not significant. However, now if we put a decimal point there and we wrote 100.0, these zeros are significant now because we have the decimal point. So therefore we have 4 significant figures. So the only way trailing zeros can be significant is if they have a decimal point at the end. If there's no decimal point, then they can't be significant. Likewise, if we go back to numbers less than 1, let's say we had a number less than 1 that's 0.004580. So again, the leading zeros are insignificant. Non-zero are significant. And then this 0 here at the end is significant. So you do have to count it when counting significant figures. So in a number less than 1, zeros to the right of the last non-zero number are significant. So that's how we determine the rules, or we determine the number of significant figures is based on these rules. Now, sometimes, depending on whether we're doing multiplication, division, or addition or subtraction, we're going to have to round our answers to the correct number of significant figures. And so when we're rounding, and the digit that we want to round, or excuse me, the digit to the right of the last digit we want to keep is 5 or more, then we just drop the remaining digits and increase that one by one. So for example, we have 2.23.678, and we want to round this to 3 significant figures. 1, 2, 3. After the 6 is a 7. So since 7 is greater than 5, we're going to increase the 6 to 7 and drop the remaining digits. So this would become 23.7. Now, if we have, on the other hand, if the digit that we want to drop is less than 5, for example, we have 40. So we have 450.635, and we want to keep 4 significant figures. After the 6 is a 3, so since 3 is less than 5, we just drop the 3 and the 5, and we keep the 6. So here the answer would be 450.6. Now it just has to be less than 5 or greater than 5. So if I do another example here, let's say we have 43.152. We want to round the 3 significant figures. So after the 1, you notice it's 5.2. So that 5.2 is greater than 5. So then we would round up the 1 to 2. It's only when the digit to be removed is exactly 5 that brings us to the third rule. So only when it's exactly 5 for the digit we want to remove, then we use this ruling here. And again, it has to be exactly 5. If it's a little bit above 5, then you're going to just round up. So again, it has to be exactly 5 after the last digit you want to keep. And so if it's exactly 5 and the preceding number is odd, we increase it by 1. If it's even, it remains the same. So for example, if we have 500.35 and we want to round it to 4 significant figures, after the 3, it's exactly 5. So since it's odd, we're going to round up to 4. So this becomes 500.4. Now, if we rewrote this number and we put 500.65, and we want to round it to 4 significant figures, we have a 6, and after the 6, it's exactly 5. So since it's exactly 5 and this is even, we're just going to drop the 5 and we'll have 500.6. Now again, it has to be exactly 5. So if we take the first number that I wrote 500.35 and instead of 0.35 I say 351, well now this is not exactly 5. This is greater than 5, so we would round up. So this would be 500.4. So again, it has to be exactly 5 for this rule to apply. Now some rules when we're doing multi-step calculations is do not round in between the different calculations. So when you take a number and use it in the next step, make sure you take, a number with quite a few more significant figures than the ones in your original answer. And only at the end do you round your final answer. So don't round in between each step. You want to round only at the end. And then the last tip is when we're doing multi-step calculations, we look at the numbers that we originally started with and determine which one is has the least number of significant figures. That will determine the number of significant figures in the final answer. And we'll be doing that a lot today when we're doing our conversions between metric and English. But just to give a few examples of rounding, so here we have 105,456. We want to round to 4 significant figures. And so here after the 4 is a 5, 6. That's greater than 5. So this would be 105,500, or you could write it as 1.055 times 10 to the 5th. Now let's say we take this number again and we want to round it to 2 significant figures. So 1, 2, it's the 0. After the 0 is 5, 4, 5, 6. So then we would round this up to now first, one of the common mistakes that students do is they'll just put 11. They won't put anything else. So if we had to round this to 2 significant figures, they would just put 11 and then forget about the placeholding or trailing zeros. But you have to include those zeros. So it would be 110,000 or 1.1 times 10 to the 5th. Now let's change the number up just a little bit. So let's say we have 103,360 and we want to round this to 2 significant figures. Well, after the 0 is a 3 and 3 is less than 5. So what does that mean? That means we drop the 3, the remaining digits. So you may want to write it like this, but this is incorrect because this shows it only has 1 significant figure. So you can't write it like this. Now if you tried to write it like this another way and put a decimal point at the end, and then this is still not correct because this has 6 significant figures. So the only way you could write an answer with 2 significant figures in it is by using scientific notation. So this would be 1.0 times 10 to the 5th. And the reason I wanted to show you this is that sometimes when you're rounding, the only way you can write the answer is in scientific notation. Because this is the only way you can write 100,000 with two significant figures. So the last thing with significant figures is when we're doing calculations, how do we determine the number of significant figures in our final answer? And so there are two different rules depending if we're doing addition and subtraction or multiplication and division. So with addition and subtraction, what we're looking at, and this is very important, we're looking at significant decimal places. And so the rule is that the answer should not have more significant decimal places than the number in the operation with the fewest. And so the reason I say significant decimal places is sometimes you can have insignificant decimal places, and we'll talk about that in just a moment. So for example, when we have 12.5, this has significant decimal places to the tenths place. But when we have 2.567, this has significant decimal places to the thousandths. And then when we get our answer, we have to round to the tenths because it's the least significant decimal place in one of the numbers in the operation. So that's why it's rounded to 15.1. Next, we have a subtraction problem, 12.5678. And so for this number, the significant decimal place is down to the 10 thousandths. Whereas our second number, 0.12, is significant decimal place is down to the hundredths. So when we get our answer, we have to round to the hundredths, and that's where we get 12.45. Now let me show you what we mean by significant decimal places. So let's say we took 50 let's see, 1 second. So say we want to do this operation, 50 plus 4.57 plus 2.300. And so 50, its significant decimal place, if you want to call it, or significant placeholder, is the tens place, because there's no decimal point here after the 0. So this 0 is insignificant. So that's what we mean by significant decimal place. So since this 0 is insignificant, only the tens place is significant. Now with 4.57, we have it to the hundredth place is significant. The 2.300, this is to the thousandths place. So since our answer, or excuse me, since the 50 is the least, has the least number of significant decimal places, when we do this operation, we're going to round to the tens place. So when I work that out, our answer becomes 56.87. So again, since 50, its significant placeholder, if you want to call it, is the tens place, we have to round to the tens place. So there's a 5, after the 5 is a 6, so we would round this to 60. Now again, this is not a very common thing, but I just wanted to stress the point that when we're doing addition and subtraction, we're looking at significant decimal places. Now when we go to multiplication and division, it's a little bit easier. We're just looking for the number in the operation with the fewest or fewer significant figures, and that'll dictate the number of significant figures in the answer. So based on those rules we talked about a few slides back, what we do when we have multiplication and division is we go and we look, we see, okay, which one has the least? That's going to dictate how many we have in our answer. So if we have here 12.34 has 4 significant figures, 3.5 has 2, and so our answer should be rounded to 2 significant figures. So that's why the answer is 43. So since both the 4 and the 3 are non-zero digits, it's not required to have the decimal point if you don't want to. You could just write 43, and that's fine. Next, we have a division. So the first number has 5 significant figures. The second number has 3. So we have to round our number to 3 significant figures. And we start with the first non-zero number when we have a number less than 1. So we go 1, 2, 3. After the 4 is a 0, so we get 0.414. So again, when we have something less than 1, so let's say we have this number here, 0.000356778. We want to round it to 4 significant figures. Some students, and this is a common problem, they'll start going at the zeros as counting them significant. So they would only write, 0.004. However, these zeros are insignificant, so you don't start counting until you get to the first non-zero number. So we have 1, 2, 3, 4. And so if we were to write the answer to this, it would be 0.0003568. So again, when you have a number less than 1, you don't include the leading zeros when you're counting significant figures. Those are insignificant. So now let's look at some problems to review. So here we have in number 1, we want to identify the number of significant figures in the following numbers. So in the first one, A, we have the unit decimeter, which is something that is measured, and we have 2,040 decimeters. So the 2 and the 4 are already significant because they're non-zero numbers. The 0 between the 2 and the 4 is significant because it's a captive 0. So 0 between 2 non-zero numbers is significant. Now this trailing 0 here after the 4, it's insignificant because there's no decimal place. And so this number has 3 significant figures. Next, we move on to the next number, and we see we have 0.005780 centigrams. Again, centigram is a unit that you can measure. So to measure grams or centigrams, you have to use a measuring device. And so we want to determine the number of significant figures. Again, the leading zeros are insignificant. They don't count. We start counting at the 5, 8, and now this 0 at the end is significant because we have a number less than 1. So this has 4 significant figures. Moving on to C. In C, we have 350 atoms. So when we have 350 atoms, atoms is something you can count. You can count 350 atoms. So since you can count it, this would have unlimited or infinite number of significant figures. And so UL means unlimited. So we know exactly it's 350.000 all the way to infinity and beyond, as that toy did, Toy Story. Next, we have 8.980 times 10 to the 8 kilometers. So kilometer is something you can measure. And this is in scientific notation, so all digits are significant. So this is 4 significant figures. And it's not a minus, it's a dash to denote the 4 goes with that. Next, we have microseconds. So microseconds, seconds is a measured number, measured quantity. And so since these are all non-zero numbers, this has 4 significant figures. And then lastly, we have 10,560 milliseconds. Second is a measured quantity. So the 1, the 5, and the 6 are significant because they're non-zero. The 0 between the 1 and the 5 is significant because it's captive. The 0 at the end is also significant because you notice there's a decimal point here. So this one has 5 significant figures. Now moving on to number 2, here we want to do the operation and determine the correct number of significant figures in the final answer. So first one we have 5.12, or excuse me, 15.12 times 25. And so the calculator gives me 378. Now, we have to round the answer to the number with the fewer significant figures. 15.12 is 4 significant figures. 25 is 2 significant figures. So we have to round this to 2, so 3 and the 7. After the 7 is an 8, so we round it up to 380. Next we have 860 plus 7.1, and when you put this in your calculator, you get 15.70. Now here we have to round, and for addition and subtraction, we round to the fewer number of decimal places that we have. And so 8.60 goes to the hundredths place, significant decimal places, and 7.1 goes to the tenths. So this answer should be rounded to the tenths place. So it'll be 15.7. Next, you see that we have a combination of addition and subtraction and multiplication and division. So when you have something like this, you need to do the operations, but all you do to round is you round to the number of significant figures that the one that has the compared to the one with the fewer or fewest number of significant figures of the original numbers. So here this one has 2 significant figures, 5.6. 12.713 has 5, and 3.56 has 3. So even though there's addition and subtraction combined with multiplication and division, the final answer is based on the numbers in the operation, the number in the operation with the fewest significant figures. So our answer should have 2 significant figures. So we'll work it out. And the computer or the calculator tells us one. So we have to round this to 2 sig figs. It becomes 5.1. And then lastly, we have another addition problem, 150 plus 5.6. So when we work this out, we get 155.6. Now you'll notice in our operations that the 150 only has a significant placeholder or decimal place to the tens place, and 5.6 has it to the tenths place. So our answer should be rounded to the tens place. So that would give us, since after the 5 is 5.6, it's greater than 5, we round up to 160. Now number 3 is just a review of what was in the last lecture. So here we have 2,500 nanometers is the average length of a bacteria. What's the length of this bacteria in millimeters? So we want to go from nanometers to millimeters, and it gives us the conversion factors for each. So what we're going to do is we're going to take nanometers, convert it to meters, convert it to millimeters. So now we need to draw our train track. So again, we're starting with 2,500. I'm going to write this in scientific notation, so 2.5. And if you don't mind, I'm going to use E instead of writing times 10. This is E to the third. So again, the capital E just replaces the times 10. So E equals this. It just makes it easier to write on this. So again, this is nanometers. Here. So since we're starting with nanometers in the next train track, we got to put the conversion factor from nanometers to meters. And since we're starting with nanometers to the left on top, nanometer goes on the bottom and meter goes on top. Now in the final train track, we're going to go from meters to millimeters. So again, on top to the left is meters, so it goes on the bottom. And millimeters goes on top. And so you see here, everything cancels but millimeter. Now notice here we're going from nanometer, which is a small metric prefix, to millimeter, which is a larger metric prefix than nano. So since we're going from a smaller to a larger prefix, our exponent's power should decrease, so it should be less than 3. And so here when we multiply, we add exponents. So first off, the 2.5 is not going to change. When we multiply, we add exponents, so 10 to the third times 10 to the negative 9th is negative 6. Negative 6 times 10 to the third is negative 3. So there's 2.5 times 10 to the negative third millimeters. And so again, this makes sense because our exponent's power decreased. And so now when we start looking at converting between metric and the English system, we need to have conversion factors to link the two systems together. And so it's very important that for each quantity, you at least remember one metric to English conversion factor so you can cross over between the two. Now for the English/standard units, it's expected that you would know the common units that we use. For example, you would know how many inches in a foot, how many feet in a yard, how many feet in a mile. Also things like how many ounces in a pound, 16 ounces in a pound, how many pints in a quart, quarts in a gallon. So those things, they should be understood, that you know them, because we use them on a daily basis. But for going from English to metric, it's important that you at least remember one for each quantity so that you can use it when needed. Now, one thing to keep in mind is that you want to pick one that you can remember, because if you go on Mr. Google, you can find out every conversion factor to fit your need. But you may not remember them because they're going to be, I like to call them exotic ones. But what we have here are some of the common ones that we can use. So remember, for metric to English, they're all measured numbers except for this inch to centimeter. So anytime you're going to use a metric to English conversion factor, you have to see how many significant figures it has, because that may limit the number of significant figures in your calculation. Now, if you use inch to centimeter, for example, for length, then this is exact, so it doesn't play a role in dictating the number of significant figures in your conversion. Now, one thing to keep in mind is that 1 decimeter cubed, if you see in volume it has decimeter cube, 1 decimeter cube equals 1 liter. So whenever you see decimeter cube, you can replace it with a liter. They're the same quantity. Another thing to keep in mind is that 1 milliliter equals 1 centimeter cubed. So anytime you see centimeter cube, you can replace it with milliliter if you need it. So make sure for each quantity you at least know 1 metric to English conversion factor. So now we're going to get into in a little bit converting between these two units. And so when we do this, it's kind of like dimensional analysis. You could say a word problem. And so we're going to be using these conversion factors to solve word problems. And so the first thing you always want to do when you have a word problem is identify what you're wanting. So are you trying to find feet? You're trying to find miles, etc. And then when you're setting, when you're looking at what you want and what you're given, make sure you pay attention to units to see how you get from what you have to what you want. And the way we do that is sometimes by making a generic roadmap to show us how to solve the problem. Once you have the roadmap, then you can see if you need any additional conversion factors or equations to solve it. And then once you set it all up, you look to see that everything cancels but the unit you want. So let's take a look at a few examples. So in the first example, we have kilometers to inches. So we want to convert 3.7886 times 10 negative 4 kilometers to inches. And sometimes in problems, it will give you a conversion factor, such as in this case, 1 inch, 2.54 centimeters. In other cases, it won't, so you have the ability to choose whichever one you want. But here we want to go from kilometers to inches, and it's giving us that 1 inch is 2.54 centimeters. So we're starting with kilometers, and we want to go to inches, and the way we get to inches is through centimeters. So the best option is to take kilometers, convert it to meters, and then convert it to centimeters, and then inches. Now bear in mind when you do this type of problem, there are multiple routes to take to get to the final answer. So if you go a different route and we get to the same final answer, no problem. So we're going to go from kilometers, we're going to find meters. From meters, we find centimeters. And then finally, from centimeters, we'll get inches. So in addition to the conversion factor we're given, we're going to need to know how many meters in a kilometer. And how many meters in a centimeter. So now we have all the conversion factors that we need to solve this problem. So we set up our train track. We start with our initial number. And again, this is kilometers. Now in the the next train track, we're going to go in our first step, kilometers to meters. So in our conversion factor of kilometers and meters, kilometers go on the bottom, meters go on top. So that's the first step, the first arrow in our path. The next arrow, we're going to go from meters to centimeters. So in our next train track, we're going to use a conversion factor containing meters and centimeters. And since meter is on the top to the left of this next train track, we're going to put meters on the bottom and centimeters on top. So now we've done the second arrow, which is go from meters to centimeters. And then lastly, we want to go from centimeters to inch. So in our conversion factor of inch to centimeter, we're going to put centimeter on the bottom. And we're going to put inch on top. And you'll notice that everything cancels out except inches. So now when you solve this, you're going to multiply everything on the top and divide by everything in the bottom. One way that you can do this is multiply what's on the top, get your answer, and then multiply what's on the bottom, get your answer, and then divide the top by the bottom. So if you notice here, if we do that, the top one is just exponents. So when you multiply, you add exponents. So this would become 3.7886. 10 to the negative 4 times 10 to the third is 10 to the negative 1. And if we multiply the two numbers on the bottom, 10 to the negative 2 times 2.54, we get 2.54 e to the negative 2. Now, what you can do here, if you don't want to put it in, use scientific notation in your calculator, is if you take 3.7886 and divide it by 2.54, you'll get the numerical part of your number in scientific notation. But you can put it in as exponents if you want as well. So we get 1.49157. And now, to get the exponent part, e to the 10 to the negative 1 divided by 10 to the negative 2. Well, negative 1 minus a negative 2 would give us 1. And so you can rewrite this as 14.9157. But we're not finished because we have to look at significant figures. So our original number had 5 significant figures. Our conversion factor of inch to centimeter is exact, so we don't have to worry about it. Kilometer to meter is exact. And centimeter to meter is exact. So our answer should have 5 significant figures. So 1, 2, 3, 4, 5. After the 5 is a 7, so we're going to round up. So our final answer should be 14.916 inches. Now moving on to the second example. Here we want to convert 5,600 pints to liters. And it gives us this conversion factor of liter to quarts. And so we're starting with pints, and we need to get to liters, and we have to go through quarts. So if we have pints, we should know that pints, there are 2 pints in a quart. So from pints, we can get to quarts, and from quarts, we can get to liters. So the only additional conversion factor that we need is to know how many pints in a quart, and that's 2 pints equals 1 quart. Now we can set up our train track. And so we're starting with 5,600 pints. So the first step in our first train track, we're going to go from pints to quarts. So since pints is on top to the left of this train track we're currently in, it's going to go on the bottom. and quarts is going to go on top. Now that we have quarts, we want to convert it to liters. So we use our conversion factor into parentheses, and we know that 1.06 quarts is in 1 liter. So now again, notice that everything cancels but liters. So now we're going to multiply everything on top, divide by everything on the bottom. And the calculator tells us 2641.509. But we're not finished. We have to see how many significant figures need to be in our final answer. So we look at 5600. It has 2 significant figures because those zeros don't have a decimal point at the end. 1 liter is 1.06 quarts, has 3 significant figures, and 2 pints is 1 quart. This is exact because it's in the English system of measurement. So we need to round to 2 significant figures. 1, 2. After the 6 is a 4, so it's just going to be 2600, or 2.6 times 10 to the third